Yeah, so thanks for the whole talk, and then we can move to our next speaker, who is Greg Valiant from Stanford University. So he is assistant professor in Stanford in the Department of Computer Science, where he's done very well-known work in algorithms and machine learning, statistics, information theory. So he has also received a number of awards, including the Career Award and a Sub-Career Award, the ACM Doctoral Dissertation Award Honorable Mention, Sloan Fellowship, Young Investigator Award from the ONR. And so today he's going to talk about some form of theoretical perspective on data amplification. So Greg, great, so you can share your screen, and please go ahead.
Okay, can people hear me?
I can hear you.
Yeah, okay, oh, perfect. Okay, well, yeah, well, thanks for the very kind introduction. Thanks for putting us together. So I'm going to talk about, I guess, what we've been calling sample amplification, which is, one way of formalizing the question of how hard is it to make data. And this is joint work with, I guess, three of my students, Brian Axelrod, Shivam Garg, and Vatsal Sharan. Okay, so I guess as a bit of a backdrop to this, I have been thinking a little bit about equivariance and data augmentation in sort of theoretical settings, but settings that might be that do overlap with practice and that are kind of not too far from practice. I guess I have these two papers. I think this paper on the right, Hong Ying is going to talk about this later this afternoon. But I'm not going to talk about these in this talk. Instead, I wanted to talk about something which is sort of motivated by some of these things, but which is really a sort of theoretical distillation of this, maybe whole question of data augmentation. So the following talk, it's it really is sort of, in some sense, pure theory. I think the insights have kind of changed the way I think about augmentation a little bit. But it'd be helpful if going into this, you don't expect to get anything that's kind of empirically relevant from this. So with that disclaimer, yeah, let me go on. Okay, so I guess augmentation is about this question of how can you kind of, given some data, how can you make more data? And if we try to distill this question of how can we actually make more data, I'm going to argue for one formalization which really tries to get to the very essence of what should we expect to do? How hard is it to make more data versus, say, the problem of learning and questions like this? Okay, so suppose we're given some data points, and we don't know the underlying distribution, but we're given a data set, and we want to understand how hard is it to make a bigger data set from this. So kind of maybe the naive approach to this would be you take the data you have. Based on the data you have, you try to learn the underlying data generating distribution. And once you've learned, say, a good approximation to this underlying data generating distribution, well, now you can draw your own samples from this and create kind of more data this way. Okay. So one very naive question is, well, is there anything else that one can hope to do? Or suppose you're given too little data to actually have any hope of learning the underlying data generating distribution. Can one still generate more data? Okay, so I should say that if there are any questions, please, I guess either write them in the chat or just unmute yourself and ask. Okay, so we kind of formalize this question of, you know, how hard is it to make more data in the following framework. So we can think about this framework as a game played between two parties. One of the parties is the amplifier, who's going to be trying to make more data. And the other party is going to be a verifier, who is going to kind of make sure that this process of amplifying a data set is sort of honest. Okay, so the amplifier gets n independent draws from some underlying distribution D. And you know, the amplifier doesn't know the distribution. They just get this, get these samples. So in this case, I guess the running example will be, suppose we think about this distribution G as being the distribution over all, you know, over all potential Renaissance paintings. Okay, so like all Renaissance paintings that were painted, and maybe even the ones that were, you know, not actually painted. So the amplifier gets n independent draws from this distribution, and we'll do something, and we'll output m greater than n data points. So these data points, you know, it could be a superset of these n input ones, or it could be some arbitrary, you know, some arbitrary function of these n data points that create m data points. Okay, the verifier is going to take these m data points and is either going to accept them or reject them. Intuitively, the verifier is the one who's going to say, yeah, these look like these could have been independent draws from the distribution. Formally, the verifier takes these m samples, is going to apply some algorithm to it, and is either going to accept or reject. However, there's the promise that if the verifier is given m independent draws from the distribution, then they must accept, let's say, with probability at least 3/4. And again, so why is this with probability 3/4? Well, even if the verifier is given truly independent draws from this distribution D, you know, maybe just the randomness of these draws yields something like, you know, something unusual, in which case it's fine for the verifier to reject. So throughout, the verifier must satisfy this. You know, the verifier can run whatever algorithm they want, provided this promise that if they're given independent draws, then they need to accept most of the time, probably at least 3/4. Okay, so crucially in this setting, the verifier knows the true underlying distribution, is computationally unbounded, so they can run some arbitrarily complex decision protocol. However, the verifier does not see the input samples that the amplifier got. Okay, the verifier only sees these m data points that the amplifier has somehow produced. Okay. Oh, right. Okay, so some of you might have recognized this fake Renaissance painting, right? So this was this, you know, so this group trained some GAN on Renaissance paintings, and their GAN painted this this painting, and this sold at Christie's for, you know, $400,000 maybe a year or so ago. Okay. Okay, so there's a two-player setup, and then we say that a class of distributions C admits an n comma m amplification scheme if the following is satisfied. So if, oops, if the following is satisfied. So if there is some amplification algorithm such that for every distribution in this class, the amplifier will be able to successfully take these n independent draws, produce a set of m samples, with a guarantee that any verifier, or every verifier, will accept these samples with good probability. So here, probability is at least 2/3. Okay, so crucially, right, verifiers need to accept perfect samples, like independent draws, with probability at least 3/4. And here there's like a little small constant fudge factor, in that we say amplification is possible if you can just you know, get the verifier to accept with probability at least 2/3. Okay. And all of our results kind of are independent of the actual choices of these constants 2/3 and 3/4, as long as they are bounded between 0 and 1, and as long as the 2/3 is less than 3/4. Okay. Are there any questions about this setup? Sorry. How do I see if there are any chats? Oh, I see.
Yeah, so it will pop up somewhere in the Zoom, right?
Oh,
now.
okay,
There
okay.
aren't any questions. But as you said,
Perfect. Okay.
everybody's encouraged to ask questions.
Okay, perfect. Okay, good. So okay, so pop quiz. Okay, so suppose D is this distribution overall, past, future, potential paintings. And suppose there's some amplifier that returns, it's given some independent draws, and it returns the original independent draws together with, say, a cropped and edited version. Okay, so in this case, it outputs the Mona Lisa, the girl with the pearl earrings, and some like edited and cropped version of the Mona Lisa. So true or false? Will every verifier accept this amplification with probability at least 2/3? Like, is this a valid amplification scheme, or is the verifier going to say, no, this is garbage?
I guess it's hard to get answers, but somebody can type something in the Q&A. Meanwhile, my question is, how large is the M? So how many cropped versions do you put per sample?
Oh, in this case?
Yeah.
Oh, so say you just had one.
I see.
Yeah, I guess the answer isn't gonna really matter. But sorry, the number of kind of in this case, the M isn't actually going to matter. Okay, so hopefully you all have some answer in your mind. So the answer is no. This is not a valid amplification scheme. Why is that the case? Well, even though this like cropped edited Mona Lisa like has a high likelihood under this distribution D, to pass the verifier, it's not enough that each of these data points we produce has high likelihood. What we really care about is that the joint distribution of all of these M distributions needs to look like M independent draws from a distribution D. Okay, and in this case, if you were to take, M actually, independent draws of the set of, paintings, you would never see a set of paintings where one of them is kind of some cropped, edited version of the other. Okay, unless you include like, forgeries and that sort of stuff in this distribution. Okay, so so in contrast to most of the, most of the thinking behind kind of data augmentation, where all you want to do is produce new data points that have good likelihood. Here, we really want the entire set that we produce to look perfect. The set of data points that we produce should be sort of indistinguishable from, a set of M independent draws from the distribution, or you can think about this as one draw from the, kind of M-wise product distribution of D. Okay. So again, so this whole framework that we were talking about, the goal is really to kind of understand this question of, can we do like perfect amplification? Like literally take a small number of data points, produce a larger number of data points that's perfect, and that it actually looks like these data points had been drawn independently from the distribution. Okay. Good. So a couple of quick properties of this. So first of all, every class of distributions admits an n comma n amplification scheme. Why is this? Well, you can just have the amplifier that outputs its n independent draws. It doesn't actually amplify at all. It just outputs its input set. And this is going to be perfect. Every verifier will need to accept this with probably at least 3/4, and that's fine. Okay, so the interesting case is where m is strictly bigger than n. Okay, another point is this kind of two-player game setting where you have an amplifier and a verifier. Up to constant factors, it's equivalent to just asking whether the amplifier can output m samples such that the joint distribution of those m samples has a small total variation distance to the distribution of m independent draws from T. Okay, so you can formulate this as either this game setting or just in terms of asking about what the distribution over these m things is. Okay, and again, the verifier does not get to see the amplifier's n input samples. If the verifier sees the n input samples and then also sees the m output samples, then amplification is equivalent to learning in the sense that if the verifier is looking at the distribution of the m output samples conditioned on the n input samples, then this is equivalent to asking, can the amplifier learn the distribution? Okay. So crucially, we're not doing this, right? The verifier doesn't see the input samples. Okay, I guess one last sort of comment. It's tempting to sort of try to think about how this is so similar or different from the GAN setting. Right? So it's very tempting to say, well, the amplifier is like the generator in the GAN setting, the verifier is like the discriminator. But this connection isn't all that. It's not all that much of a connection. Again, because typically in GANs, the discriminator is just looking at each. They're looking at the images kind of one by one, or in small sets, as opposed to evaluating the entire set of generated samples. And then also, the discriminator in a GAN setting gets to see the training set. It gets to kind of see the n input samples to the verifier, to the amplifier. So this connection to GANs is, there's some sort of connection, but it's not a tight connection. Okay, so let me give a flavor of some of the results that we can show. So the first theorem is, suppose C is the class of all discrete distributions supported on at most k elements. Then, given n input samples, there is an amplification scheme that can produce n plus n over square root k output samples, and that's optimal. So what does this actually mean? So this means that given, as soon as you're given square root k samples, you can start to do non-trivial amplification. You can start to actually produce larger data sets. And so surprisingly, square root k is much less than the sample complexity of actually learning the distribution. If you want to learn, an arbitrary distribution supported on at most k elements, say it's a small total variation distance, you do need on the order of k samples. Okay, and it's sort of a different result that ends up looking quite similar. Suppose C is a class of Gaussians in d dimensions, say with a known, or say isotropic Gaussians, but with an unknown mean. Then again, n comma n plus n over square root d amplification is possible and optimal to constant factors. So again, this means that given square root the dimension samples, you can start to produce larger sets. even though learning this learning this Gaussian, learning the mean accurately enough that you get, say, small constant total variation distance requires on the order of the dimension samples. So in both of these cases, yeah, I guess I was extremely surprised that one can actually increase the size of our data set long before we have any idea of what the distribution is. So before we have any hope of learning the distribution, we can still kind of make more data in a perfect fashion, in a way that nobody can distinguish the slightly bigger set from from honest samples from the distribution. Okay, so I'll say a bit more about these things, but I guess the big punchline is that yeah, this amplification is actually quite a bit easier than learning. That you need far less data. Okay. So let me just talk a tiny bit about this Gaussian setting. Okay, so yeah, as I said, you can start this amplification given only square root of the dimension samples, but learning requires on the order of d samples. And we actually have this other theorem that we showed, which is that if the amplifier is forced to output a superset of the input, so namely the amplifier is forced to output the n independent draws together with some new stuff mixed in, then actually amplification doesn't happen, or it's not possible until you have almost linear in the dimension samples. So until you have d over log d. So let me sketch the intuition for why this theorem 3 is true, and that'll actually provide an intuition for how we, for the algorithm that achieves theorem 2. Okay, so why is it that if you're forced to output the input samples together with some new stuff, why is amplification much harder in this setting? Well, the issue is intuitively that the new things that you produce, they're either garbage, in which case the verifier will say, look, there's garbage there, I reject, or the new stuff you produce is kind of obviously too correlated with the original samples, in which case, again, the verifier will say that's garbage. So like in this example, suppose our amplifier produced these 3 images. The verifier would, even if the verifier kind of didn't know what these images were, the verifier would say, I reject this. This is obviously garbage. This middle image, it's too correlated to the other 2. Like all you did was take the girl with the pearl earring and photoshopped on the Mona Lisa's face. You can guess which slide took me the longest time to make. Okay, and again, so in this Gaussian setting, we can actually formalize this in the sense that if you're forced to output the input together with new stuff, either the new stuff is kind of bad, is like obviously like so far from the right distribution that the verifier can just reject, or it's kind of the new stuff looks good, however, it's too correlated to the other stuff, in which case it sort of is revealing the fact that it was fabricated. Okay, so the algorithm that amplifies starting at the square root dimension regime, it's basically you create this bad setting, and then you decorrelate each of the original examples from the new stuff. So if we're trying to do n comma m amplification, we draw the kind of additional m minus n things from our best guess of the distribution. And then, actually, I'm sorry. We draw them from the best guess of our distribution, but shrunk back so that we're sure that these samples aren't too off. And then they're much too correlated with the original samples. And then for each of these original inputs, we kind of decorrelate it from the stuff we've created. And then we return the decorrelated things together with the new things. Okay. Yeah. So yeah, I guess that's all I wanted to say about the kind of intuitions and the proofs behind these results. If you're interested to look at the paper, okay, so I guess at the beginning I said that this was really just a kind of theoretical thing. Is it actually useful? So crucially, amplification does not add any new information, right? We're taking n independent samples. The amplifier has no idea what the distribution is, and is kind of taking these n samples and producing more of them. But the larger set of samples is a function of these n samples. There's no new information there. So whatever kind of, if you have an information theoretically optimal algorithm, there's no point in using amplification. However, it can make the information that's present in the original samples somehow more easily accessible, right? So it's like it's taking the information in these n samples and kind of spreading it over some larger set. So if you have some like statistical estimators that are some heuristic things or some that are kind of widely used but not optimal things, then in some sense you can always do this, apply an amplifier, and then apply your statistical estimator. And because this amplification scheme is like information theoretically perfect, in that no one can distinguish the amplified samples from good samples, this kind of can't, this can never do any harm. Okay, maybe I won't go through this example. We do have some concrete settings where using not optimal but commonly used estimators, amplification does give us some yardage. Okay, this is a joke. How do we take one paper and turn it into lots of papers? This is not what we want to do. Okay, that said, though, I guess there are lots of what I think are really interesting questions. So I said both for these discrete distributions of a given support size and d-dimensional Gaussians, we can do amplification is much easier than learning. There's certainly lots of distributions for which amplification is no easier than learning. You can only start to amplify at the point where you can start to learn the distribution. And in general, a nice question is, well, what property of a class of distributions determines the threshold at which non-trivial amplification is possible? So we have lots of ways of describing how hard it is to learn things. And it seems like this amplification threshold is sort of orthogonal. Like, it's not like some nice function of, the distribution complexity and some standard notion of that. Okay, maybe I'll, it's also worth thinking about, either say more powerful verifiers. So, if a verifier can peak a little bit at the input sample of the amplifier, at what point can we reduce amplification into learning? And one maybe particularly interesting question is, what happens if our verifier is less powerful? What if the verifier doesn't know the distribution, but only gets some samples from it? What's the landscape of amplification there? And maybe most related to questions of kind of data augmentation and and learning is this question of, what if the verifier is computationally bounded in the sense that the verifier only interacts with these amplified samples via a learning algorithm? So this is kind of borrowing the kind of terminology or the kind of intuition from pseudo-randomness. So in complexity theory, the pseudo-randomness basically is the study of how do you take a small number of truly random bits, produce a larger string of things that look random, and how do you quantify whether these larger number of bits look random? Well, you argue that with respect to different bounds on the computational power of kind of the verifier, computationally bounded verifiers cannot tell the difference between this longer string of pseudo-random bits and actual random bits. And this is kind of the same question. So if you have, just a specific class of learning algorithms, and the verifier only gets to look at sort of what these learning algorithms are doing with the data, can it still tell that her amplified samples are amplified as opposed to actual independent samples? Okay, so that's all I have. Yes, thanks.
Okay, great. Thank you, Greg, for this really puzzling, very interesting talk. So I, encourage everybody to ask questions. I also have a question. So in this Gaussian mean example, basically everybody who is in that example knows that it's a Gaussian mean example, right? So they know that it's that they know the explicit form of the density that's involved, and the only parameter is the mean. So in that setting, I was thinking whether is it somehow connected? I was just trying to connect this kind of a theory that you proposed, developed to like other things that I know about, and in particular, like, is it connected somehow to shrinkage estimators? Because they're, like, for instance, just plugging in the sample mean, we know that even though it's like minimax rate optimal, it's not the best estimator, and it can be uniformly improved upon by something like sign shrinkage. And I was wondering if somehow that's what's going on, or not really, or like any other intuition that you have and connections to other things. Yeah.
Yeah, no, that's a good question. So So yeah, I guess it's a little bit different than these sorts of shrinkage things. So so again, this the sign shrinkage is this again kind of counterintuitive thing that if you're say someone gives you say there are 3 Gaussians, one-dimensional Gaussians, each of a different mean, Gaussian A, Gaussian B, Gaussian C. If you're trying to estimate the mean of A, the mean of B, and the mean of C, and given one sample from each of them, you can do better than just outputting the the sample from A, the sample from B, the sample from C. You can do slightly better by kind of shrinking those 3 samples towards their overall mean. I think it's fairly different in the sense that in those kind of shrinkage type things, you're you are kind of explicitly trying to learn this distribution, right? You're trying to learn the you're trying to learn the means. I guess I would say, like, certainly in the case of the discrete distribution, there's no sort of analog of the sort of shrinkage thing. So I think it is a little different. Although I guess maybe one of the common themes is that as soon as you start caring about either joint distributions or kind of estimating these higher dimensional things, like some counterintuitive phenomena do start to rise even in the learning setting. But I think it's other than the fact that they're both kind of surprising, I think it's and I should say that the we are trying to kind of generalize results to like general exponential families, and and sort of try to get a bit more structural sense of what drives the threshold at which amplification is possible. But it doesn't seem to fit neatly within any
and partly just because you were showing that linear regression example, and the very obvious way where you can do better than the obvious linear regression estimator, there is some sort of ridge regularization, and that could be like a classical estimator, and obviously some sort of appropriate regularization would do better in finite samples. So it felt like maybe there's a connection, but it doesn't look like there's a connection, right?
Yeah, I mean, again, so this is this thing of, suppose you have labeled examples and you're trying to estimate the error of the best linear model in the regime where you don't really have as much data, you don't have enough data to really find the best model, but you want to estimate what the error would be if you were to get more data and then learn that. So yeah, I mean, this kind of classical scaled version of the least squared model, it's unbiased, but it's not anywhere close to being information theoretically optimal. Yeah, so maybe it's not surprising that you do get some benefit. But then again, if you think about our learning algorithms, I would argue that it's likely that our learning algorithms are even further from being kind of information theoretically optimal than any of these kind of simple statistical things. So
Okay, great. Yeah, thank you very much for the explanation. And you can always, so the audience, you can always ask direct questions afterwards.